Hi, ladies and gentlemen. You may recall earlier in the week, we did some derivations of some area formulas. We're going to take another look at the triangle area formula today, but we're going to do it a little bit differently. What you may recall is that when we analyzed the area formula the first time for a triangle, it relied on knowing the base length, but it also relied on knowing the height or the altitude of the triangle because the height hits at a right angle. Well, we're going to look at what's called Heron's formula today, named after the mathematician who founded it. Okay, and what this does is it allows us to find the area with only the three sides. Or in other words, if we didn't know the height, that would be fine. In order to do that, we're going to have to also label some other parts of this diagram. Now, what I've done for you today is I've provided you a Kami document on a Google Doc that just had a blank title in case you want to do your notes digitally, but you'd have to flip back and forth between the video and that or split screen it. You also have the option to just follow through with loose leaf if you'd like. But getting this down for yourself, going through the motions might be important because I might ask you to reproduce this or at least understand the reproduction of this on your own and how things develop. It's going to use a lot of your algebraic knowledge that you already have from previous courses and a little bit of stuff from this year. Now, we're going to take these details and we're going to add to them. So in this, we're going to call the other two sides A and C so that the three sides are just nice common variables, A, B, and C. Okay, notice the overall triangle is not a right triangle necessarily. This is for any triangle. So I'm not saying that A and B are the small ones and C is the large one. Okay, it's just this overall triangle is any triangle. So we're just going to call any three sides A, B, and C. I don't care about their size. However, in order to utilize the two right triangles that the height does split this one into, what we're going to end up doing is calling one of these pieces X, and we'll call the other one B minus X. No need to use another variable because that would just be B, take away the other portion. And this allows us to have three important things for us to analyze. Three givens, if you will, based off this diagram. And some other knowledge. Given number one is that area formula that we already know about. That area equals 1/2 base times the height. Another piece of information that can be given is how we use Pythagorean theorem for these two right triangles. The one on the right, if we filled in Pythagorean theorem, would be x squared plus h squared equals c squared. And if we did the same for our third given with the right triangle on the left-hand side, that would be the leg of b minus x getting squared, the other leg, which is the height being squared, equal to the other side of our triangle, a squared. So we're going to take these three sets of givens and we're going to manipulate them a little bit to try to figure out what Heron's formula is. Or in other words, to try to rewrite given number one so that height is no longer required. And instead, it's only going to be written with A's, B's, and C's. So let's do a little bit of work on this first one. Okay, sorry, this second given, so that we can solve for x. So if we subtracted h squared from both sides to try to not have to have x involved anymore eventually, we would end up with x squared equals c squared minus h squared, which is going to be an important fact for us. And also what x itself is. So if I took the square root of both sides, x is also c squared minus h squared. Another important fact for us. That's why I put it in a different color. Okay, sort of along the same veins of trying to simplify one of my givens before I use it completely, I could maybe simplify this a little bit. I could do double distribution for this b minus x squared. So if I double distributed that, that would be b squared minus 2bx plus x squared with the rest of it, plus h squared equals a squared. Okay, and so I have that restructured to use a little bit. If we keep going with this, what we're going to be allowed to do, okay, is we're going to move things around, and since we know what x squared and x are equal to, we're going to go ahead and substitute in for them. Now, because I know how this is supposed to work out, I'm going to get a little bit ahead of myself just to make it look nicer for you on the page. I'm going to add 2bx to both sides. There's a reason for it. Okay, you'll see why. Okay, but b squared plus x squared plus h squared now equals a squared plus 2bx. And we're going to take given number 2. We're now going to focus on those two locations I just underlined in purple. We know what those are equivalent to. So I can say b squared plus, instead of x squared, I can write c squared minus h squared. And then on the other side, instead of the 2b being multiplied by x, it's a little messy, but I can multiply it by the square root of c squared minus h squared. You might notice what happens on the left side for us. On the left side, we now have a minus h squared and a plus h squared. So that's going to allow us to rewrite this as b squared plus c squared. And on the other side, have a squared plus 2b, the square root of c squared minus h squared. Okay? We now have something conveniently that x is now no longer a part of, even though I introduced x myself into this. Okay? But it's not there anymore. So our only goal now is to try to get rid of h. So I need to start isolating h. And you did that last year. They were called literal equations, where we would solve for one variable in terms of a whole bunch of other variables. It was another thing under our manipulation category. So I'm going to start getting h by itself. So I'm going to subtract a squared from both sides. So that's going to give me b squared plus c squared minus a squared is equal to 2b times the square root of c squared minus h squared. Oops, I wrote b. Sorry, h squared. Now, there is a problem with the fact that it's stuck under a square root. Okay? You could technically divide the 2b on both sides right now and then square it. Okay? But I'm going to take this opportunity now to just square both sides so that I don't have to square a fraction. So I'm going to square both sides. I'm not even going to bother rewriting the left side. There's a reason for that we'll see in the future. So I'm just going to write that entire side as just being squared. And on the other side, technically, this is monomial-like in the fact that we have just a 2 times a b times this entire square root. So we can pretend that when we square it, it's just 2 times 2, which is 4, b times b, which is b squared, and the square root times itself, which just cancels the square root out. So that just becomes c squared minus h squared, freeing the h variable from the square root that it was in. At this stage, we can go ahead and divide both sides by 4b squared. And I'm going to take this opportunity of this division to be the moment where I move to a new paper. So what we're going to do is we're going to have these 4b squareds reducing each other out. And I will now have this written as b squared plus c squared minus a squared, all squared, divided by 4b squared, equaling just c squared minus h squared. So now we're getting a little bit closer to h being isolated all on its own. So what can we do now? Well, I actually want to swap some things around. Okay, so what I'm going to do is I'm going to take the minus h squared and I'm going to move it over to the right side by adding h squared to both sides. But I'm also going to take this large fraction and move it to the other side by subtracting it from both sides. So I'm going to subtract b squared plus c squared minus a squared, all squared, over 4b squared on the other side as well. I'm not being lazy. I could have just maybe drawn the arrows and said, hey, go ahead and switch them. But we actually should show that additive property of equality on both sides. Okay, so that's going to lead to them swapping locations. So I'll have only the h squared on the left, and then I'll have the c squared minus this fraction on the right. Now at this stage, these are all algebraic rules that you've learned so far, but you may want to find yourself pausing, going back, re-looking at something, and then coming back to this stage in the video. So we just passed the 10-minute mark. So if anything was a little fuzzy, you might want to rewind and look at it and then come back to this, okay? So do that if you need to, okay? But I'm going to continue on. And I'm going to try to make this into a common denominator with the other piece. So what I can do is I can multiply the top and bottom, which is technically just a 1, by a 4b squared. And so now I have them with a common denominator. So I can write them together. H squared would equal 4b squared c squared minus, parentheses, b squared plus c squared minus a squared, close parentheses, all squared. And that's all over 4b squared. Okay. What I can do now is a factoring method that you learned last year with the numerator of that fraction. Take a second, look at the numerator of that fraction, see if you can figure out what that could be factored with, like what method. I'm just going to wait a second. You might notice that it's a difference because it's a subtraction problem, and both things on the left of the subtraction and on the right of the subtraction are squares. This is a dots question, difference of two squares. I can take h squared and I can rewrite it, okay, this numerator, as 2bc as one of the factors, and the other factor as just what was in the parentheses, 1 with an addition, 1 with a subtraction. So I can add the entire parentheses b squared plus c squared minus a squared, and also subtract the entire parentheses b squared plus c squared minus a squared. And that's still over 4b squared. Okay. What I'm going to do is I'm going to now remove the parentheses that this large piece was around. Okay, and I'm going to do that by distributing the positive to the one on the left and distribute the negative to the one on the right. So h squared will now equal parentheses 2bc plus b squared plus c squared minus a squared. And the other one will be 2bc minus b squared minus c squared plus a squared. So I changed the signs of everything in there. Still all over 4b squared. Okay, so we did our dots factoring with the numerator, but because one of these squared pieces had multiple parts, I just took a second to distribute out the addition and subtraction that we get from dots. Okay, I'm not going to do too much other stuff in this next step with you, but what I am going to do is use the associative and commutative properties to move around and regroup some things. Okay, so I'm going to just edit the way this looks a little bit, and I'm going to make this first parentheses turn into b squared plus 2bc plus c squared minus a squared. So all I did is I used commutative property to switch those two locations. In the other parentheses, I'm going to do a little bit more than just that. I'm going to do the a squared, move that first, and then I'm going to put the minus b squared plus 2bc minus c squared. So I did a lot more commutative property there. Still all over 4b squared. And now the associative property is going to come into play. I'm going to group things together. So on the left-hand side of these two dots questions that I've been rearranging, what I'm going to do is I'm going to group the b's and the c's together. So b squared plus 2bc plus c squared. That's isolated from the minus a squared. And I'm going to do that over here as well. The a squared, I'm going to isolate from this. Now the catch is, just like the one on the left, I could rewrite this as a subtraction. The problem is that I'll have to change all of the signs of the things that I'm grouping together. So if I want to view this as one giant subtraction problem, I have to view that as subtracting a b squared, subtracting a negative 2bc, and adding a c squared in there, because if I distributed that negative, they would be their opposite sign. So to group them with associative property, I had to do that. Okay? Sorry, that 2 was not supposed to be there on the outside. Let me just make sure that. Okay. So we did a dots question. I rearranged a whole bunch of stuff, and the purpose of me rearranging that for you was because I actually have now created 2 more dots questions, whether you realize that yet or not. Okay, that's the situation at hand, because with those parts that I put in parentheses because of the associative property here, I can factor them. They are what are called perfect square trinomials. B squared plus 2bc plus c squared is just b plus c being squared. If you look at double distributing that, there would be a b times a b, there would be a c times a c, and there'd be 2 b times c's. That happens in our other one as well. This other parentheses inside of our first dots factoring is just b minus c squared. Because a b times a b is a b squared. A negative c times a negative c is c squared. And you would have 2 b's times negative c's, resulting in the negative 2bc. And so because of that, I'm going to use this as another little transition moment. I can now refactor these again with dots. So one of them is going to end up being, here, let me get the denominator in. One of them is going to be ending up as a b plus c plus an a. The other one is going to be a b plus c minus an a. Then on this one, we would have an a plus a b minus c. And we would have an a minus a b minus c. And so if I try to just look at what those are and rearrange them in alphabetical order, should I want to do that? Yeah, I'll do that. We would have a plus b plus c. We would have a negative a plus a b plus a c. Here we would have an a plus b minus c. And here we'd have an a minus b plus ac. All over 4b squared. So you can see every single one of these has all 3 variables. The first one, they're all positive, but then in each of the second, third, and fourth ones, one of them has a negative sign with them. Kind of unique situation that we find ourselves in here. Okay, so at this point, I'm going to do a little side note. Perhaps I should have put it in the givens, but kind of like an indirect proof, it's important now, so I'm almost going to mention these items now. It's important to note that any polygon has something called perimeter. We usually represent it with a capital P. So in this case, the perimeter of this triangle would have been a plus b plus c. There's also something called semi-perimeter that we usually denote with a lowercase s. Semi-perimeter is just perimeter halfway around the shape. Okay? So the semi-perimeter of this triangle is just a plus b plus c divided by 2. So what I'm going to do is use this knowledge of semi-perimeter just being the perimeter divided by 2 and knowing what perimeter is to help me out a little bit more with some of this manipulation that I'm doing. Okay, now that we have from earlier these 4 factors in the numerator, I'm actually going to do some more manipulations to each of them. Okay, inside of the first one, okay, I actually don't want to do anything. It looks nice and pretty as it is because that happens to be the perimeter already. However, in this one, I don't have the perimeter because one of the variables is negative. So what I'm going to do is I'm going to put in a positive a, and I'm also going to put in a negative a. So I'm going to add in a positive a, and I'm going to add in a negative a into this. Okay. I know that seems counterintuitive because now I'll just have another negative a with the plus b plus c. But I'm allowed to do this for anything I want to because I've really added nothing because I added a positive and a negative of the same feature. Okay, I'm going to do that for the other ones as well that have the negatives. So in this case, it's the a plus the b, and then I'm going to add in a positive c, I'm going to add in a negative c, and there was already a negative c there. And if I do that over here, I'd have a plus b minus b minus b plus c. Okay, so in each of these, I've just added one positive and one negative of those same variables. It's still all over 4b squared. Now, using those properties, okay, what I'm going to do is rearrange once again. So I have these, okay, but now in each of these parentheses, I still have another a plus a b plus a c. Here's an a, here's a plus b and plus c. But what I have left over in addition to the perimeter is minus 2 of the original negative variable. So over here, let me swap these as well so that we have a's, b's, and c's in order. This would be a plus b plus c minus 2b's being negative. And this one would be a plus b plus c minus 2c's because we have 2 negative c's in that one. All over 4b squared. Okay, what I can rewrite this now as is we have the perimeter times the perimeter minus 2a times the perimeter minus 2b times the perimeter minus 2c all over 4b squared. And it's finally time for us to take the square root of both of these sides. So we would know that the height of this figure is equal to the square root of p times p minus 2a times p minus 2b times p minus 2c all over, that actually we could take the square root of, that's just 2b. Now, we have height. It was 2 pages of notes ago where we had some givens introduced. And one of those givens was the fact that the area of a triangle could be described as 1/2 times the base times the height. Well, we're going to take that info now, and we're going to take what we just defined h as, okay, and we're going to rewrite some things. So instead of area being 1/2 times base times height, area is 1/2 times base times this lovely expression, the square root of p times p minus 2a times p minus 2b times p minus 2c all over 2b. The b and this b will reduce each other out. The 2's don't, they're both in the denominator. Now we have area is equal to the square root of the perimeter times p minus 2a times p minus 2b times p minus 2c all over 4. What we actually want to do, might seem counterintuitive, is get that 4 back underneath the square root. So if you square a 4, it becomes a 16. So a 4 put back underneath a square root would end up being a 16. So this would be a giant square root fraction of the p over p minus 2a times p minus 2b times p minus 2c all over 16, because that's now inside the square root. Okay, but that's the same thing as if I had given each of these individually a little division of 2, because 16 is just 2 times 2 times 2 times 2. So I could rewrite each of these little perimeter-based expressions over their own little 2. But as we stated before, when perimeter is cut in half, that can be called the semi-perimeter, or that can be S. So the area of a triangle is better known as the square root of P divided by 2, which is semi-perimeter, S, P minus 2A divided by 2, which becomes the semi-perimeter minus A. Then P minus 2B divided by 2 is the semi-perimeter minus B. And P minus 2C over 2 is the semi-perimeter minus C. So this is the area of a triangle when S is equal to the semi-perimeter, or A plus B plus C divided by 2. This is better known as Heron's formula. It was a lot of work to get here, and it is one of the most advanced derivations we do in this class. Okay? Now what I'd like to do is show you an example problem of why this is used. It's going to be, once again, a little bit weird because I'm going to show you an easier problem to do without Heron's formula first, but you're going to see this in action with a situation that's better to describe it in a second. So example number 1 for me to look at with you. Okay, I'll draw a triangle where we know that the base of this triangle is 14 and the height of this triangle is 12 units. Okay, since I gave you the base and the height, great. You can use your original area formula for this if you would like. However, I will also let you know that when the height came down, it split the base into pieces of 5 and 9, and also with sides of the triangle 13 and 15, which will also allow us to use Heron's formula for this example. Okay, so option number 1 for this, okay, will just be 1/2 base times height, which of course is going to be easier for this example because that's just 1/2 of 14 times 12, or whatever 7 times 12 is, which is 84. So 84 square units would be the area of this. Heron's formula is more complicated for this one. Okay, option 2 being Heron's formula, we would need the semi-perimeter first. So the semi-perimeter is 13 plus 14 plus 15 divided by 2, or in other words, 21, because when we add all of these together, we get 42 as the perimeter. Half of that, the semi-perimeter, is 21. So we also know that the area of a triangle can be described as the semi-perimeter times the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. So the area of this triangle can also be described as the square root of 21 times 21 minus 13 times 21 minus 14 times 21 minus 15. So the area of this triangle can be 21 times 8 times 7 times 6. That happens to be the square root of 7,056 if you multiply all of these together. And that is just another version of 84 square units. You're saying to yourself, great, I did that by listing the formula, substituting in, and I got my answer right away with option 1. Here I had to figure out what semi-perimeter was before writing my formula, plugging in, then going ahead and writing out some more work to finally have something under a square root to find. That was more work. Well, that's because I happened to give you height for this question. There are going to be examples out there and problems where the height is not given to you, such as this situation. Example 2. Okay, here I have no idea what the altitude or the height of this triangle is. And if I don't give you angle measurements, you're not going to know either. So I'm just going to say that the base is 23 and the other two sides are 8 and 16, which 8 plus 16 is 24. It's bigger than 23. It's definitely a triangle that can exist. So what we would do in this scenario is be forced to use Heron's formula. So we would need to know the semi-perimeter, or in other words, we would need to know 8 plus 16 plus 23 divided by 2. So if we add these up and divide by 2, it would be 23.5. What we would be able to do now is take that the area of a triangle is the square root of S times S minus A times s minus b times s minus c. So the area of this triangle is 23.5 times, okay, and then s minus a is 23.5 minus 16. S minus b is 23.5 minus 23. And s minus c is 23.5 minus 8. Okay? Or in other words, the area of this triangle is equal to the square root of 23.5 times 15.5 times 7.5 times a half. Okay? We can also put these in parentheses if we want to make it look a little nicer. Okay, this, go ahead and type into your calculator for a second and turn it into a fraction, because that'll be a little easier to work with for you. So go ahead and multiply all of those decimals together and turn it into a fraction. You should get 21,855 all over 16 if you did it correctly. Which, if you take the square root of that, unfortunately, the top cannot be simplified. The bottom, the 16, can. So we would say that the area of this is radical 21,855 fourths units squared. Most typically, you'll be told to round these answers. Or they'll work out nicely, like in the case of the first one. But there was a necessity for this, okay, when there were buildings going on that had triangular structures in them, supports, where the height just couldn't easily be calculated. All right, so Heron's formula was manipulated and invented basically by a mathematician to figure out the area of a triangle where you couldn't easily figure out its height or you didn't have any way to obtain it. All right, so I know this was about a half hour of a derivation just to lead us to two different things, but I wanted you to see that there was purpose to you learning all of those manipulations from last year, and here's a practical effect of that in geometry. All right, you have a homework sheet, so if you have any time left, I know you might have rewound the video a little bit and then come back, but if you have any time left, go ahead. The homework should be posted for you to now take a look at, okay? If it is towards the end of the period, then you just can complete that on your own tonight. Okay, I will see everyone again in class tomorrow. Thank you.